Hi everyone, my name is Justin Cross and this is my homework 3 for Transport 1. The question we were given is, we see a wooden log, we assume it's a perfect cylinder, and it is floating in some water and it's sticking up above the water at height h. What we want to do is find the density of the log such that it floats in water at that certain height. Now we look at the log and we first think, what do we know? Or what can we assume? Well, what I'm going to assume is that there is no acceleration on the log. So A equals 0. Just like that. And because of this assumption, we can say that any force pushing down on the log, say a gravitational force, has to equal any force pushing up on the log, say a buoyant force. So we start by writing that down. The force of gravity, F of G, is going to equal the buoyant force. I'm going to call that F of B. Now, what are these forces? Well, the first force we know, it's just the mass of whatever is being pushed down times the acceleration due to gravity. So that becomes the mass of the log, which is being pushed down. We're going to call that M of L times G. Just like that. And now what is the buoyant force? We use the same methodology and we say the mass of the water that was displaced by the log times the acceleration due to gravity equals the buoyant force. So M of the water, I'm going to call that M of W times G. That is what our buoyant force equals. Now we have some cancellations here. We cross out both of these accelerations due to gravity. And what we're left with is the mass of the log equals the mass of the water displaced. Now we want this in terms of the density, right? That's what we're solving for. Well, converting mass to density is pretty easy. You just add a volume there at the end. So our mass of the log becomes the density of the log, so rho of L times the volume, or the volume of the log, V of L. And that equals, using the same methodology again, rho of W times V of W. Just like that. Now we can solve pretty easily for the volume of the log. Because it's a cylinder, we have an equation for that. But the volume of the water that was displaced isn't as easy. And that's going to be the majority of this question. So solving for this volume of the log, we have the rho of L times pi r squared times the height, or in this case, big L, equals rho of the water times, and then the volume of the water which is displaced is this cross-sectional area below the surface of the water, like that. I'm going to call that A, C, W, or cross-sectional area of the water, times the length to get the volume. Now again, get our red marker out. We have some more cancellations here. The length actually does not matter in this equation. And what we're left with, if we want to put it in terms and solve for the density of the log, rho of L, the density of the log, equals the density of water, rho of W, times cross-sectional area over pi r squared. What we want to do with this equation, it's basically almost done. What we want to find is the cross-sectional area of the water. Now I'm going to draw one end of this log here. Perfect circle, just like that. That's pretty good, actually. We'll find our center point, about right there. We'll find the height at which the water sticks out, just like that. That's our H. We've got a radius here. I'm actually going to draw a couple more radius, just like that. Those are all the radius. And what we want to find is the cross-sectional area of the water, or everything below here. Using some geometry, we can actually find that pretty easily. So we start with ACW, a cross-sectional area of the water, is going to equal the whole thing, so pi r squared, the whole area, minus just this top portion right here. I'm going to call that the segment. The segment. You'll see why I paused there on a little bit. So the segment segment equals, if we want just this top portion, we can find the sector, or this ice cream cone shape, and subtract the triangle. I'm going to call that A of S for the area of the sector minus the area of the triangle, just like that. Now if we plug that into this first equation, we get the cross-sectional area of the water, ACW, equals pi r squared minus the area of the sector plus the area of the triangle. Now we know pi r squared, that was given. What we don't know is the area of the sector and the area of the triangle. And we're going to solve for those now. So if we start part 1 here, area of the sector, there is an equation for this. It's going to equal the angle that we're looking at over 2 pi times pi r squared, just like that. Now I'm actually going to manipulate this a little bit. Instead of one big angle here, I'm going to split it up into 2 equal angles. I'm going to call them theta, just like that. And that affects our equation here. Instead of theta, it is 2 theta, just like that. And again, we've got some more cancellations. If I find my marker, this 2 and this 2 cancel out, this pi and this pi cancel out. And what we're left with, A of S equals theta times the radius squared, just like that. Now, what is theta? We can use a little bit of trigonometry to solve for that. This is why I decided to split up that angle into 2. So we have a theta right there, we have an r right here, and what is this length here? The vertical part here. Well, we know this is r, and we know this is h. So to find everything that's not h in that radius, it is r minus h, just like that. Now, because we know our geometry and we know our trigonometry, we know that our cosine of theta equals the adjacent, so r minus h, over the hypotenuse, in this case, r, just like that. Now, we can say that because of that, theta is going to equal inverse cosine, so cosine to the minus 1 of that value, r minus h all over r, just like that. And now with this new equation for theta, we can plug it into our area of our sector, and we get area of the sector equals r squared times inverse cosine minus 1 of r minus h over r, just like that. That is part 1 of filling in this equation. The next part is to solve for the area of the triangle. So we go part 2. Area of the triangle equals 1/2 base height, right? That's elementary. Now, if we look at this, what is our base of this entire thing? Well, we call this up here, we'll just call that x for now, because we don't know what it is yet. So the whole base is 2x. So area of the triangle equals 1/2 times the base, 2x times the height, in this case is r minus h. So r minus h, just like that. And then again, we've got some more cancellations. This 1/2 and this 2, they multiply together and give us 1. Now, what is this x? We can find this x pretty easily because this, in fact, is a right triangle. And using Pythagorean's theorem, we can state, we'll just do this here for a moment to separate all this, x squared plus r minus h squared equals r squared. Or if we solve out this and solve for x with a little bit of algebra, we get x equals the square root of r squared minus r minus h squared, just like that. And then if we simplify a little more, we get x equals the square root of 2rh minus h squared, just like that. Now we can plug in this formula for x into our area of a triangle, and we get area of the triangle equals r minus h times the square root of 2rh minus h squared, just like that. And that is the second value that we wanted to plug into this equation. Now that we have everything for this equation, we can actually substitute our area of the sector and area of the triangle in and get the cross-sectional area of the displaced water. So let me write that down here. It'll be a handful. So A, CW, cross-sectional area of the water, equals the entire area of the circle, pi r squared, minus the area of the sector, so r squared inverse cosine minus 1 of r minus h over r, plus the area of the triangle, r minus h, square root of 2rh minus h squared. Just like that. And now that we have the cross-sectional area of the displaced water, we can plug that into the very first equation we have, solving for the density of the log. So if we do that, we get the density of the log, rho of L, equals the rho of water, which is usually given, rho of water, I'm just going to put that there for now, times this cross-sectional area. Let me write this down. Again, it's a mouthful. So pi r squared minus r squared inverse cosine of r minus h over r, this is inverse, plus r minus h square root of 2rh minus h squared. I hope this is legible. All over pi r squared. Just like that. I'll close parentheses here. And that right there is actually our completed density of the log. What we've done is we have found the density of the log in terms of three things: the density of water that it's in, the radius of the log itself, and the height at which the log is above the water.